Hi, my name is Valerie Marshall, and today I will be teaching you how to use the chain rule for integration, aka U-Substitution. A little bit about me: I am an actuarial science major here at Utah State University, and I work as a mathematics and statistics tutor here at the Aggie Math Learning Center. Of course, before we learn U-Substitution, we need to know why it's important, and that is because U-Substitution is an important skill to have when solving integrals. This of course begs the question, why are integrals important? Integrals are important in countless real-life situations, including calculating the area between curves, distance, velocity, acceleration, volume, work, kinetic energy, probabilities, and many other things. So it is clear they are important and have real-life applications. So, how do we do a U-Substitution? I will teach you how in 4 parts. Part 1 is establishing necessity. This means looking at the integral and making sure a U-Substitution would be helpful. Then once necessity is established, we find our u and its derivative du dx. Then we can plug this u back into our equation and change our bounds so they're consistent with the changes we made to our equation. And last, we solve the integral. For the first step, establishing necessity, we look at the integral and make sure it has some term f of g of x. I like to call this term a fox in a box term because it has one equation that is inside the other. The outside equation, or f of x, is the box, which has g of x, the fox, inside of it. Once necessity is established, and we know there is some f of g of x term in the integral, we then take out the g of x term and say that term will be our u. Then we take the derivative of g of x to get g prime of x dx, and because g of x is u and the derivative of u is du, we then know that du is equal to g prime of x dx. For our third step, we plug everything back into our equation. So our g of x is u, so f of g of x is now f of u. And by some basic algebraic manipulations, we know that dx equals 1 over g prime of x du. So we can substitute that in for dx. Lastly, we need to change our bounds to be consistent with our U-Substitution, and we do this by plugging each bound into u, aka plugging them into g of x. So a becomes g of a and b becomes g of b. Last, we solve. Now, solving this integral may seem a bit tricky at first. Sure, the f of u is just a basic equation, but there's that pesky 1 over g prime of x that seems to be a problem. This problem is regularly resolved in one of 2 ways. Either the original integral had some g prime of x term so that when you plug in d of x is equal to 1 over g prime of x du, then the prime of x's cancel, or it's also common that g prime of x is some c, where c is some constant real number, in which case you can simply take it out and multiply it by the integral. Let's do some examples. Our first example is the integral from 0 to 1 of e to the 4x dx. In this case, our larger equation, our box that contains the smaller equation, or our f of x, is e to the power of x. Our smaller equation in this case is 4x because it replaces the x that would usually be in the exponent of e to the power of x. So the box, or f of x rather, is e to the x, and the fox, or g of x rather, is 4x. Now we take out our g of x, which is 4x, and we say that will be our u. Then the derivative of 4x is simply 4, so the derivative of u is du, or 4 dx. This can be algebraically manipulated to isolate dx by simply dividing each side by 4, so that 1/4 du is equal to dx. Then we just plug everything in. 4x is u, so instead of e to the 4x, we just have e to the u, and dx is 1/4 du, so instead of dx, we have 1/4 du. And because 1/4 is a constant that can be moved out to the front of our integral, we do that. Lastly, we change the bounds to be consistent with our U-Substitution by plugging them into our g of x. G of x in this case is 4x, so 4 times 0 is 0, and 4 times 1 is 1. Now we're in terms of u, and we can solve the integral. The integral of e to the power of u is just e to the power of u, and we make sure to keep our 1/4 out front. Then we can plug in our bounds, and we know that e to the power of 0 is just 1, so we end up with 1/4 times e to the power of 4 minus 1, which is approximately 13.3995. Let's do one more example. In this example, we have the integral of 6 times 3x squared plus 4 all squared. In this case, we see that our f of g of x term is 3x squared plus 4 all squared. So our outside equation is x squared and our inside equation is 3x squared plus 4. Then we take out our inside equation and make sure that it is u. So then g of x is u and u is 3x squared plus 4. Then we find the derivative of that is 6x. So du is 6x dx, and by algebraic manipulation, that means 1 over 6x du is equal to dx. Next, we plug everything back in. U is 3x squared plus 4, so we know we just have u squared. When we plug in 1 over 6 du for dx, the 6x's cancel, and we're left with just the du. In this case, there are no bounds to change. Then we solve the integral. By power rule, u squared becomes 1/3 u cubed plus c, and then we simply plug in 3x squared plus 4 for u and get 1/3 times 3x squared plus 4 all cubed plus c as our answer, where c is some constant real number. So, as a recap, to do U-substitution, all you have to do is first make sure it's necessary, then pick your u and find its derivative, then plug that u back in and change the bounds, and finally solve the integral. This was Valerie Marshall on U-Substitution. If you'd like to learn more, these are great resources which I used in my research for this topic. Hope to see you soon.